Okay, so now we're going to get into chapter 5, and in chapter 5, we will be concerned with how do we go about naming compounds. So that's what nomenclature is all about. Now, when it comes to deriving or determining the names of substances, compounds, elements, etc., there are two systems or there are two ways of naming these compounds. We have what is known as the common naming system, and then we have the systematic naming system. Now, the common naming system or the common names are derived primarily from the properties displayed by these different substances. So they're not really based on the composition of the substance itself. All right. So as stated here, they're based on some observable and outstanding chemical or physical property. In chemistry, however, we prefer to use systematic names. And the reason why we prefer to use systematic names is because by looking at the name, you can tell the composition of the compound. And also, if you know what the chemical composition of the compound is, you can determine the systematic name. And that is not possible when it comes to the arbitrary names based on chemical or physical properties. Now, the systematic naming system is actually devised by an organization called the International Union of Pure and Applied Chemistry, abbreviated IUPAC. In fact, it's a division of this organization that meets on a regular basis to basically decide and agree on naming compounds. So, this is a list of different substances and their formulas and their chemical names along with their common names. So, to the left, you have the common names. And if you look at the common names and compare it to the formula, you'll see that, there's very little link or indication as to the composition just based on the name. So, for example, lime is CaO, that's a formula. One cannot tell the name or one cannot tell the formula based on the name. However, if you look at the chemical name calcium oxide, well, you can see the connection between the name and the formula because calcium oxide tells you that this particular substance is made up of two elements, calcium and oxygen. All right, so, and you can see the same thing in other examples listed here. Okay, so we're going to get into some details about how we go about naming certain elements and compounds, and we'll be discussing ionic compounds, so that's why you see here elements and ions. So, when it comes to naming elements, the formula for most elements will be the same as the symbol for that element. And that is true in the vast majority of cases. So, these are just a few examples. So the formula for sodium is Na, and that's basically the symbol you're going to use. The symbol for potassium is shown, and so on and so forth, all the way down to calcium down here. All right, now there are some elements that exist in nature as diatomic molecules, and we mentioned these before, all right? And this is important because whenever you're given a question where you have these elements, for example, involved in a reaction or undergoing some process, you have to understand that we're not just talking about the monatomic version, we're talking about the diatomic version. So whenever you see a question where you have these elements involved by themselves, uncombined with anything else existing in nature, then you need to remember that these are diatomic, all right? And there are two elements that are polyatomic. In other words, their molecules each contain more than one atom. Sulfur exists as S8, 8 atoms per sulfur molecule, and phosphorus exists as P4, 4 atoms per sulfur molecule. Again, you need to memorize these, all right? Okay, now as far as ions are concerned, we were introduced to it briefly before. We talked about ions being basically atoms or collection of atoms that end up with a charge by the addition or losing of one or more electrons, all right? So that's what ions are. Now, what we'll be talking about here is the formation of monatomic ions, ions formed from just one atom. Now, it says here an ion can be produced by adding or removing one or more electrons from a neutral atom, and we're going to see some examples of this. The first example is that of the potassium atom. The potassium atom has 19 protons and 19 electrons. And what happens is that the potassium atom tends to lose one of the 19 electrons, and you're going to end up with 18 electrons, right? So we end up now with a structure which has one more proton than electron, and therefore has a net positive charge. And this symbol here indicates that K plus, the plus indicate that there's one plus charge, and therefore we call this the potassium cation, right? A cation is basically a species which has a positive charge. So that's what we call that. We call a positive ion a cation. Okay, and there are several other examples of cations that are known to be formed from their respective atoms. Sodium will lose one electron to form the sodium ion. Calcium will lose 2 electrons to form the calcium ion. And aluminum will lose 3 electrons to form the aluminum ion. And later on, we're going to learn how can we determine how many electrons can be lost from an atom to form the respective cation. Okay, how do we name cations? It's very simple. It's basically the name, same name as their parent atoms. All right, so for example, the sodium ion, which is formed from the sodium atom, is called the sodium ion, right? The ion that is formed from the calcium atom is called the calcium ion. The ion that is formed from the lithium atom is called the lithium ion. The ion that is formed from the magnesium atom is called the magnesium ion. The ion that is formed from the strontium atom is called the strontium ion, and so on. All right, so it's not complicated. Basically, the name of the cation is the same as the name of the atom from which it is formed. Okay, now let's talk about the negative ions, which are known as anions, and these are formed when you have the addition of one or more electrons to a neutral atom. So as an example, we'll be using the chlorine atom, which contains 17 protons in the nucleus, 17 surrounding electrons. And what will happen in this case is that chlorine will tend to gain an electron to form a species which now has 18 electrons. The number of protons still remain the same, so therefore we end up now with a negative ion where we have one more negative charge than positive charge. So this is called the chloride ion. All right. So this is of course an anion because, as we said before, an anion is a negatively charged ion. How do we name anions? Well, it's a bit different from naming cations because basically to name an anion, what you do is that you take the stem of the parent element name and then you add an IDE ending. So all the names of these monatomic anions end with IDE. So fluorine becomes fluoride. All right. Chlorine becomes chloride. Bromine becomes bromide. Nitrogen becomes nitride. Phosphorus becomes phosphide. Oxygen becomes oxide. So and so on and so forth. So basically, when naming anions, you take the stem name of the original element and you simply add IDE to it. So their naming always ends with "ide." Okay, so ions are always formed by adding or removing electrons from an atom. Most often ions are formed when metals are combined with nonmetals, and this is typically how ionic compounds are formed. They're formed as a result. Now there are a few exceptions to this, but we'll get into that later on. But in the main, basically, whenever you have a metal combining with a nonmetal, we have the formation of an ionic product. And the charge on the ion can be, to some extent, not always, but to some extent, predicted based on the position of the element in the periodic table. So if you look at this table right here, what you'll notice, this is a version of the periodic table. What you'll notice is that elements in groups 1A, 2A, and 3A, they tend to form ions equal to the group number, all right? Well, I should say ions that have charges equal to their group numbers. That's what I meant to say, all right? So basically all elements in group 1A, they tend to form ions of a +1 charge. Elements in group 2A, they tend to form ions with a +2 charge. Elements in group 3A, they tend to form, 3A, they tend to form ions with a +3 charge, all right? Now, when it comes to elements in groups 5A, 6A, and 7A, you can determine the charge of the anions formed from these elements by taking their group numbers and subtracting from it 8. So therefore, nitrogen and phosphorus, they tend to form ions with a -3 charge, because 5 minus 8 gives you -3. Elements in group 6, they tend to form anions with a -2 charge, and that comes about as a result of 6 minus 8, giving you -2. And then finally, elements in group 7A, they tend to form ions with a -1 charge, and that comes about as a result of 7 minus 8 gives you -1. Okay, now when it comes to elements in the transition region right here, it's very difficult, in fact near impossible, to predict the ionic charges. So therefore, what I just mentioned concerning groups 1A, 2A, 3A, 5A, 7A, and 6A does not really apply to the elements in this region here. All right, and it is for that reason why I provide a chart in Canvas, which includes, among other things, the list of common ions and their charges. All right, so you'll have that to refer to basically solve problems such as what we're going to learn about shortly. How do we determine the formulas for ionic compounds? Okay, so that's what we're going to talk about, writing formulas from the names of ionic compounds. So what we're talking about here is a situation where if you're given the name of the ionic compound, how do you determine the formula? Now, the key thing that you need to remember is what you see here on the screen. This is, I would say, the most important and fundamental thing that you have to recognize when it comes to naming these compounds, and that is that a chemical compound must have a net charge of 0. And what that means basically is that the total number of positive charges in the compound must be equal to the total number of negative charges. All right, so to illustrate this, we're going to look at these examples right here. Our task is to determine the formula for these compounds, right? So the first one is calcium chloride. So as I said before, you'll have access to the tables, and if you look up the formula for a calcium ion, you see that the formula is, let me write it here, Ca2+, all right? And the formula for the chloride ion is Cl-. So you see here that we have a +2 charge here, we have a -1 charge here. As we said before, the charges must cancel out, right? The total charge must be 0. So in order to achieve that in this case, what you would do is multiply the number of chloride ions by 2. And therefore, when you put this together, this is how you do it. The formula for the product, or for this compound, would be CaCl, and the 2 that is here now becomes a subscript down here. And that will be the formula for the calcium chloride. All right, so that's how you do that. Now for the second one, it's the same principle. The first step, you go to the tables and you look up the formula for barium, which is Ba2+, and for the phosphide ion, which is P3-. So we have a +2 charge here, we have a -3 charge. How do we get the charges cancel out? We need a 3 here, and we need a 2 here, right? So that we have a total of +6 as far as the bariums are concerned, and a total of -6 as far as the phosphide ions are concerned. And therefore, when you put these together, each of these numbers that we multiply the ions by become subscripts. So therefore, barium phosphide formula becomes Ba3P2. All right, and one thing I should point out here at this point, when it comes to writing down the final formulas, you'll notice that in the case of calcium chloride and barium phosphide, there are no charges present in the final formula. All right, so even though you have charges present actually in the compound, but when you're writing down the formulas, there should be no charges indicated. You just write down the formula and include the subscripts for the number of ions present in the formula. Okay, this last one, magnesium oxide, again, you go to the tables and you look up the formula for magnesium, which is Mg2 plus, and the oxide, which is O2 minus. And this one is easy because basically we now have a situation where the total number of plus charges is equal to the total number of negative charges. So therefore we don't need to multiply each of these ions by anything. All we have to do is put them together and the answer becomes MgO. And that's it. Alright? So that's basically how you'll determine the formula for your compound based on the names of your ionic compounds. Alright, we're going to stop here, and the next video we'll be dealing with some more naming of ionic compounds because things become a bit more complicated, especially when transition elements are involved. Alright, so until next time.